Hello and welcome to Stories of Science. Here, we look back on humanity's long journey to understand the world. The questions, the failures, and the breakthroughs that slowly changed how we see the universe and ourselves. We tell science as stories. The theory that almost broke physics until one man fixed it. If I told you that modern physics, at one point, collapsed, you'd probably think I'm talking about some sci-fi plot. But wait. This isn't just a bit complicated. It's not a little tough. No, the calculations came back as infinity. Pause for a second. Yep, the kind where you open your bill, ready to check how much you have left, and see this. Balance, infinity. You wouldn't be smiling. You'd be having a meltdown. And that's exactly the face the physicists of the time had. They'd worked for hours, writing formulas, deriving pages of equations, only for the answer to be insanity. The mass of the electron? Infinity, the charge correction? Infinity, the entire theory? Just like a buggy program crashes the moment you run it. And the thing is, this was supposed to describe the most fundamental laws of the universe. When it crashed, the whole of modern physics pretty much got a blue screen of death. So, here's the question: who fixed this disaster? Who turned infinity back into something usable? You might have heard the name. Maybe you haven't. Shinichiro Tomonaga. But here's the crazy part. When he did this, he wasn't in some top-tier lab. Not in some academic hotspot. He was, essentially, offline. No access to the latest papers. No international conferences. No equipment. Imagine this: while the rest of the world was upgrading their software, he was still running on the old version. But somehow, in that situation, he fixed the universe's code. Sounds pretty unreal, right? Like he had some secret cheat code. But here's the thing: he had no cheat code. He was just different from the start. This story begins in a not-so-normal family. He was born in 1906 in Tokyo, Japan. Seemingly a pretty regular year. But the family? Not so much. His father? A philosopher. Not the writes essays kind of researching the meaning of existence kind. You can imagine the dinner table at a normal family's house. Hey, what's for dinner? Should we order takeout? What time do you start work tomorrow? Normal stuff, right? But in his house? It was probably more like, what is consciousness? Is the world really real? Why do we even exist? Yeah, a kid hearing this at the dinner table. What do you think that does to a person? Simply put, he didn't take the world for granted. He started questioning everything. When everyone else saw an apple fall and thought, gravity. He might have wondered, why does it have to fall? Could it not fall? Who decided it has to fall? Sounds a little annoying, right? But that's the starting point of science. Doubt, not disbelief, but questioning everything. That's the environment he grew up in. No one handed him the right answers. Instead, they kept asking questions. And asking more questions. It was like debugging a program. There was no "this is how it is." Only, why is it like this? You could say, he wasn't just naturally smart. He was habitually unsatisfied. While others learned knowledge to remember it, he learned it to tear it down and rebuild it. This was crucial because, later on, when quantum electrodynamics started breaking down, it was a new framework that was needed. You either accept the crash, or you rebuild. And this ability didn't pop up overnight. It was forced out of him from a young age at the dinner table. Sometimes, it's not the environment that helps you win. It's the one that teaches you not to fear failure, not even fear flipping everything upside down. Back then, he hadn't written world-changing theories. He hadn't won any awards. He was just a kid, bombarded by philosophical questions every day. But it was that kid who, years later, when faced with infinity, didn't run. Didn't break. He just quietly thought, if the world isn't right, then let's fix it. And that is where the real story begins. His life soon introduced him to a key NPC. Flash forward to his student days. Time: Kyoto, Japan. Location: a school. Two young men, sitting in the same classroom. They seemed pretty ordinary. But, if you move the timeline forward, you'll realize, this classroom? It's got some serious future impact. One would predict a particle that's never been seen before, the other would fix an entire theory. In short, one was creating new characters. The other was debugging the game. Their names, Shinichiro Tomonaga and Hideki Yukawa. Yeah, the guy who went on to win the Nobel Prize. But at that time, they were just students. Still, their vibe was already a little off. Let's talk personalities. Yukawa was more than intuitive genius. He'd suddenly say, "I think there should be a particle here." Everyone else would be like, "Huh." He'd just say, "I feel it." Then there's Tomonaga. He was the opposite. He'd say, "Wait, let's check every step carefully." He didn't trust gut feelings. He trusted the logic had to be clean. One was like an artist, the other, like an engineer. One was drawing the future, the other, fixing the present. You can imagine their daily lives. While the teacher lectured, Yukawa might be spacing out, but not daydreaming. He was inventing the universe in his head. Meanwhile, Tomonaga's writing out full pages of calculations, then looking up and asking, "Is this assumption correct?" Suddenly, the whole class gets awkward. "Teacher, please don't do that." But that's exactly why they made such an interesting contrast point. One was bold with ideas, the other, careful with logic. In the same classroom, pure gold. The coolest part, they were solving different problems. Yukawa would later tackle, where does force come from? He proposed the meson theory, explaining why atomic nuclei don't just fall apart. Tomonaga, on the other hand, had a much bigger disaster to face. The whole theory was unworkable. One was answering why is there structure. The other was answering can this theory still be used. They were on different paths, but their goal was the same, to understand reality. It might sound grand, but back then, they were just two young men, arguing by the chalkboard, erasing equations, losing sleep, then doing it all over again the next day. No one knew that decades later their names would be written together in the same chapter of history. And no one knew that they would face the same enemy in different arenas, the unknown. Let's move the timeline forward a bit. Back then, the heart of science wasn't in Japan. It was in Europe, especially Germany. That was the headquarters of quantum mechanics. If science were a game, the scientists there were the game developers. Tomonaga, he decided to take a trip. Not to follow a tutorial, but to meet the people writing the code. It was the early 1930s. He set out for Europe. This wasn't a casual study abroad trip. It was more like plunging straight into the core dungeon. Germany at the time had gathered a group of world changers, and standing at the forefront, Werner Heisenberg, the one who proposed the uncertainty principle. A co-author of quantum mechanics rulebook. Think of it like this: he wasn't researching the game. He was writing the rules. Most students go abroad to attend classes, do experiments, write papers. But Tomonaga, he was more like, I finally get to meet the dev team. That realization? It's hard to describe. Because in Germany, you finally realized, the world might be nothing like you thought it was. In classical physics, the world is continuous, like a smooth line. You walk from A to B. Every point in between is there, feels right, comforting. But in quantum mechanics, nope. The world is discrete, like steps. Or, even more extreme, when you're not looking at it, it doesn't even exist in a defined state. Sounds like mysticism, right? But this is cutting-edge science. When Tomonaga first encountered these ideas, it was shocking, not difficult, but every intuition you've ever had gets flipped on its head. What you thought was true, turns out, it's all wrong. Time, not absolute. A position, not fixed. Particles, not really particles. Waves, not entirely waves. The whole world, shattered then pieced together in a weirder way. Most people, in his shoes, they'd take a step back, too abstract. I'm out. But he didn't. He was more excited, because when the rules are unstable, that means you can rewrite them. So, he learned, absorbed, questioned, and rebuilt. And in those top labs, he didn't just sit in class. He observed. He watched how the rule makers thought, how they handled contradictions, how they tackled the impossible. This experience was crucial, because when quantum electrodynamics finally collapsed, Tomonaga didn't panic. He'd seen it before. Rules can be redefined. Problems? They're just the entrance. And now, he was standing right at the door. But the world wasn't about to let him keep learning in peace. Time rolls forward to 1939. And a much bigger system update began. It went by the name of World War II. Sounds like history class, right? But for scientists back then, it was a forced shutdown. Especially for someone like Shinichiro Tomonaga. He had just come back from Europe. He'd just met the dev team. He was just getting ready to jump back into the global conversation about the rules of the universe. And then the server went down. International collaboration stopped, papers no longer circulating, conferences cancelled. Can you imagine it? What was once a global team working together to debug the universe, now, suddenly, the internet was cut, everyone stuck in their own little rooms. And in Japan, it was even worse. Resources were scarce, equipment lacking, the conditions for research crumbling. Elsewhere, scientists were still talking and debating if fixing each other's work. In Tomonaga, he was in offline mode, totally cut off. No latest updates. No peer feedback. No someone's already tried this direction reminders. It sounds pretty grim, right? Like writing code without access to the web. You can't check references, you can't ask anyone, all you can do, think for yourself. And the problem he was facing, one of the most complicated theories of the time, quantum electrodynamics. It was already full of infinities, and now, the discussions had vanished. Many people, in that situation, would have said, let's just wait for the war to end. And you'd get it, right? It makes sense. But Tomonaga didn't. Instead, he did something even stranger. He kept thinking, and the deeper he went, the more questions he uncovered. Sometimes, the world's too loud, you can't hear the key problems. Everyone's talking in new theories, different opinions, constant debates. You can easily get swept up in all of it, but when everything goes silent, no papers. No conferences. No outside input. You're left alone with one thing: the problem itself. No reference answers. No standard paths, just you and those infinities. It's lonely, but also pure. So he started to break things down, step by step, asking the most basic questions. Where are these infinities coming from? Which ones are physical? Which ones are just a result of our mathematical methods? Sounds tedious, right? But that step, it was like stumbling through darkness. No light, but you start remembering where every stone is placed. Little by little, a path began to appear. And during all this, the world outside, it didn't get any better. In fact, it got worse. The war escalated, resources were even tighter, research conditions even worse. Now, he had to face another problem: survival. During the day, his research, it was no longer purely theoretical now, it was directly serving the war effort: radars, electromagnetic waves, and that era's crucial device, magnetron. To put it simply, it's the core component that made radar more efficient. You can think of it as how to better detect the enemy. It sounds very real, very urgent, even a bit brutal. But here's the interesting part: these engineering problems actually pushed him to dive deeper into theory. During the day, he was figuring out how electromagnetic waves spread, how they reflected, how to amplify them, how to stabilize the equipment, all practical problems. But at night, it changed. He'd sit back at his desk, staring at those formulas, those infinities, and start asking a different question: what's the rule behind these phenomena? Daytime, figuring out how to fight a war, and nighttime, figuring out how the universe works. It sounds like running two threads, and both threads, not simple at all. But this back and forth, it showed him something. Engineering problems force you to face reality, theoretical problems force you to understand the essence. Point one tells you how to do. The other forces you to ask, why? When both threads come together, you start to notice something: many of those infinities, maybe they're not a problem with the universe, maybe it's a problem with the way we describe the universe. This was a crucial turning point. Not in a fancy lab, not in international conferences, not amidst heated debates, but in an environment where resources were scarce, information was isolated, and everything was a bit chaotic. That's where it began to grow. Sometimes, real breakthroughs don't happen in the best conditions, they happen when you've got no way out. No internet. No colleagues. No references, only the problem, and that's exactly why he started hearing things that were drowned out by the noise before. Those tiny logical gaps, the assumptions that were overlooked, the obvious steps. One by one, he picked them apart, checked them again, redefined them. And in the ruins, he didn't stop, instead, he started rebuilding. And this time, it wasn't about patching things up. It was about preparing to completely rewrite the rules. But the problem didn't get any easier just because he stuck with it. In fact, it only got more outrageous. By the mid to late 1940s, the entire physics community was facing a massive mental blow. It had a fancy name: quantum electrodynamics. In simple terms, it's the theory that describes how light and electrons interact. Sounds basic, right? And it is basic. But here's the catch: it couldn't be calculated, and I don't mean a little tough. I don't mean slow to solve. I mean it literally just blows up into infinity. Let me say that again: it's not an occasional mistake. You sit down, derive the formulas step by step, fill up page after page, and then the last line, infinity. You'd probably think, did I mess up somewhere? And at first, so did everyone else. So they checked, then rechecked, threw it out, started over, tried a new method, and the result, still infinity. Now, imagine what the physicists of that time felt. Am I just not cut out for this? Maybe I should start farming. At least plants don't produce infinity. That's no exaggeration. It was a collective crisis. Because this theory wasn't just some corner case. It was the core theory explaining electromagnetic phenomena, which means the light you see, the electricity you use, even the screen you're looking at right now. It's all in that theory. If it breaks, it's not just a problem with one formula. It's a sign that the entire framework is unreliable. And here's the weird part: the experiments were fine, the measurements were spot on, they matched the real world perfectly, but the theory, boom, exploded. It's like you have a machine that works perfectly, but then you open the manual and it says, here should be infinity. You wouldn't feel comfortable with that. You'd start wondering, am I using something that no one really understands? That was the infinity crisis of the time. It wasn't that they made a mistake. It was that, after solving the equations, they started questioning everything. And Tomonaga, he kept moving forward. He had been thinking in the ruins for a while, but now he was facing the core issue. What are these infinities? Do they even exist, or is it our way of describing them that's flawed? Many try to just erase them, like spotting a bug and thinking, delete it. But the problem was you couldn't delete them. They weren't just random errors, they were showing up systematically, meaning the problem lay deeper. So, Tomonaga switched gears. If infinity couldn't be erased, could he understand it differently? This was a crucial, almost counterintuitive step, because it meant he wouldn't treat infinity like an enemy. Instead, he'd treat it as a signal. A clue that told him where the problem lay. He started redefining some of the most basic quantities, things like the mass of an electron, things like charge. In classical physics, these were fixed, they were just there. But in the quantum world, things weren't that simple. An electron isn't just a little ball floating around. It's surrounded by a cloud of virtual particles. These particles keep popping into existence and annihilating each other. It's like a constantly vibrating boundary. That means the mass you measure for the electron isn't just the electron itself. It also includes all the quantum fluctuations around it. And here's the kicker: if you try to add all these contributions together, of course, it's going to go haywire. Of course, it'll blow up into infinity, because you're trying to fit an infinitely complex system into a finite number. It just doesn't work. So what did he do? He did something clever. He didn't try to remove the complexity. Instead, he redefined what we were actually measuring. To put it simply, he drew a distinction between two types of parameters. Point one was the bare parameters, the raw values in the theory. The other was the observable parameters, the values we actually measure in experiments. The key point here: we only care about the latter. We don't need to know what the original electron looks like, because, frankly, you'll never measure it. You can only measure how it behaves in reality. So he absorbed all those infinities into these new definitions. Sounds abstract, right? But think of it this way: you have a bunch of scattered phis, infinite phis, you can't calculate them. What he did was, alright, let's bundle up all these phis. Let's package them into a new total price. That total price is finite. And it's the real price you need to pay. Now, the infinity didn't vanish, but it was tamed to put into a place where it wouldn't wreck the calculations. And that's when the idea of renormalization was born. He didn't eliminate infinity. He did something harder: he taught humanity how to live with infinity. It sounds a bit philosophical, but it was incredibly practical, because once he did that, the whole theory suddenly worked. You could recalculate and no longer get infinity. Now you had a real number point 1 that you could compare with experiments point 1 that could be verified and one that could continue to develop. In that moment, it was like a program that had been crashing nonstop, suddenly ran smoothly. No one was staring at those infinities anymore. People started using the theory to make predictions to explain phenomena to build more complex models. And Tomonaga, in that almost offline mode, step by step, he built this method up. No forums, no discussion groups, no latest papers. Just him and a bunch of formulas that seemed beyond saving. He didn't run away. He didn't delete the problem. He just changed his perspective, and then he got the whole physical world back on track. Now, here's the interesting part. While Tomonaga was in offline mode, slowly taming those infinities, on the other side of the world, someone else was doing almost the exact same thing, and they had no idea about each other's progress. Fast forward to the late 1940s. The war was over, the network was back online, papers started flowing and news started spreading. And then, something weird happened in the scientific community. Point 3 people, point 3 different approaches, point 3 completely different methods, and yet they arrived at the same answer. These three were Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga. Now, let's talk style of Feynman. He was like a genius hacker. He didn't follow the usual rules. He'd just draw pictures, use those diagrams to calculate, elegant, intuitive, even a little casual. Schwinger, the complete opposite, extremely meticulous. He'd work through equations line by line, every step as clean as a machine. And Tomonaga, he took a middle path. He had structure, but with flexibility. He reorganized the entire theory from different angles. 3 people, point 3 languages, point 3 ways of thinking. If this were an exam, it would have been a funny sight, the 3 of them sitting in different classrooms, writing 3 completely different answers. Then the teacher takes them in and looks at them, and they're all correct. And the crazy part, they all match. What does that mean? It means this theory wasn't just made up. It wasn't just close enough. It actually got to the core of the problem. Because no matter which path you took, you still ended up at the same conclusion. That's extremely rare in science, and it's incredibly important. That moment, quantum electrodynamics, no longer a problem. It became a tool. And one of the most precise tools at that. So precise, in fact, that it matched experimental results to several decimal places. Sounds a little wild, right? But that's the reality. A theory that was once full of infinities now became one of the most accurate theories in human history. A true turnaround in physics. And these 3, they went on to win the Nobel Prize together. Different paths, same answer, like 3 people climbing different paths up a mountain, only to meet at the top, look at each other and say, "You made it too?" And then, together, looks like this mountain is real. But the story doesn't end there. Because what comes next, it gets even more interesting. You might think, these theories, they sound high-level, they sound abstract, far removed from everyday life. But the truth is, you're using them right now. Yep, right at this moment. As you scroll through your screen today, you're holding a phone with the screen lit up, the visuals are smooth. You're watching videos, liking and commenting, everything seems natural. But behind the scenes, quantum electrodynamics is running the show. First, let's talk about the most critical part. Semiconductors, the transistors in your chips, control the flow of electricity or the behavior of these electrons. It's not something classical physics can explain, the way they move, the way they interact. You need quantum theory for that, and those parts that once caused infinities, now, tamed and turned into precise models. Without it, no modern electronics. Without it, your screen would stay black. And then there's laser technology. When you go to the store and scan a barcode, that beep sound, the red light, that's not regular light. That's a laser, highly uniform, super precise. And the creation of that light, it depends on quantum jumps, another core part of quantum electrodynamics. No quantum theory, no laser. What about MRI scans? The machines at the hospital. You lie down, the machine hums, and out comes a clear internal image. Behind that, the behavior of atomic nuclei and magnetic fields, the fine structure of electromagnetic interactions, and once again, it's all built on that same redefined theory. So, think about this. Remember when I said, you're using quantum electrodynamics as you watch videos? I wasn't kidding. It's true. Those infinities that once made physicists crack, now, They're part of your everyday life, you don't even notice, but they're there running smoothly. Like a backstage system you've never seen. No interface. No alerts, but once it breaks, the whole world freezes. And behind all of this, there's a man in the most chaotic of times, in an almost offline world, who fixed the system step by step. When the dust finally settled, and you look back, you'll realize something a bit mind-blowing. That theory, the one that used to blow up every time you tried to calculate it, it's now one of humanity's most reliable tools. That's quantum electrodynamics, folks. How accurate is it, you ask? Well, here's the thing in physics. There's this well-known benchmark, the magnetic moment of an electron. Sounds niche, right? But the measurement precision? Off the charts, so they can measure it down to several decimal places. Now, the theoretical calculation, it uses that very framework, the one that used to be all infinities, and the result, it matches, not close enough. Not within error margins, but literally matches. It's like you wrote a program, and the output is 0.123456789012345. Then you look at the real-world number, and it's 0.123456789012345. You stare at it for a few seconds, and you start to wonder, am I in a simulation? That was the shockwave through the scientific community. For the first time in human history, we described reality this precisely, not the big stuff, not roughly, but down to the last decimal. This is monumental in science. So, what does it mean? It means that this theory, it's no longer just about explaining. It's become a mirror of reality. The formulas you write on paper are almost perfectly aligned with what happens in nature. This, in the history of science, is rare. It's almost like a once-in-a-lifetime discovery. And behind all of this, there's a key path. It started with a collapse and ended with rebuilding, and on this path, Tomonaga Shinichiro walked the most quietly, but also the most determined. But if you ask, what did he leave behind? The answer isn't just formulas. It's not just a set of equations. More importantly, it's a mindset, the ability to create order in chaos. When the world seems unreasonable, most people will doubt the outcome. A few will doubt the method, and even fewer will rewrite the definitions. What he really said was, maybe it's not the world that's wrong. Maybe it's our way of asking the questions. Sounds like philosophy, right? But it changed science. Because of this, post-war Japan's physics community started to develop its own identity. It wasn't just following the crowd. It was now defining the path. A generation began to rise. Voices from Japan started being heard on the world stage. From Hideki Yukawa to countless other scholars, a thread slowly took shape, and one of its sources, it lay in that offline era. One person, without references, reorganized the entire problem. You could say he didn't invent the universe. He didn't change how the world works. Electrons still move the same way, light still travels the same way, nothing looks different, but one thing is completely different now. We finally know what we're looking at. He didn't change the world. He changed how we understand the world. Remember that question we started with, that theory that once collapsed, that thing that, every time you tried to calculate it, would blow up into infinity. What's it become now? It's one of humanity's most accurate tools, from system crash to smooth operation. But here's the thing, there was no miracle. There was just one person. In the quietest of times, step by step, he re-asked the questions. That person, Tomonaga Shinichiro. He didn't delete the errors. He didn't shy away from complexity. He just changed his angle, and then everything realigned. Right now, as you scroll through your phone, everything feels smooth, natural, but under the surface, that once chaotic set of rules, it's running quietly. No prompts. No pop-ups. It won't even tell you, once upon a time, this was infinite. And that's what makes it so powerful. It didn't make the problems simpler. It made complexity coexist. So if one day your life feels like it's in total chaos, plans falling apart, emotions all over the place, everything feels wrong, don't rush to throw it all out. Don't rush to doubt yourself. Maybe you're just not done with your renormalization yet. Some infinities aren't mistakes. They're just reminders. It's time to redefine things. I'll leave you with this: the universe never gives you the answers, but there will always be someone who figures them out. The people who change the world usually just think one step deeper. If this story made you see things differently, hit like, subscribe, and save it. See you in the next story.